The following question describes a situation in which a student swings a ball of mass m attached to a string of radius r in a horizontal circle with an initial tangential speed v naught. The student then proceeds to decrease the radius by pulling the string inward. The question then asks what will happen to the angular momentum and rotational inertia of the ball about about the axis of revolution when the string is pulled inward. The answer I chose was A, which states that the angular momentum increases while the rotational inertia decreases, which is wrong. To start, when the radius decreases, the angular speed increases. This is evident from the following equation: V equals omega r. If you solve for W or omega, you'll find that omega equals V over R. Now in this equation, if you were to decrease R, then you will see that omega increases as a result. Given that angular velocity increases in this situation, we can now apply this to an equation that expresses angular momentum in order to find out what happens to rotational inertia. And the equation we will be using is L equals I times omega, where L is angular velocity, I is the rotational inertia, and omega is angular speed. In this equation, we know that from our situation, L remains the same because there are no torques applied and omega is increasing. In order for L to remain constant while omega is increasing, I must be decreasing. Now we know that in the following situation, as the radius is decreasing, the angular momentum will remain the same while the rotational inertia will decrease, which is the same explanation as choice A. Therefore, choice A is the correct answer. The following question describes a situation in which a uniform ladder of mass m and length L rests against a smooth wall at an angle theta naught. The question then asks what is the torque due to the weight of the ladder about its base. In order to answer this question, we can use the equation for torque, which is torque equals radius times perpendicular force. Here we can identify the axis of rotation as the point of contact between the ladder and the ground. Given this information, we can identify the radius as length over 2, since the length from the contact point between the ladder and ground and the base of the ladder is length over 2. Next, we know that the force is going to be mg, since the question is asking what is the torque due to the weight of the ladder about its base. However, we must use a component force of mg that is perpendicular to the radius. As you can see, there are two components, sine and cosine. The component that is perpendicular to the radius is the cosine component. Therefore, f is going to be mg cosine naught. When this equation is put together, we get that the torque is equal to mg L cosine of theta naught all over 2. Part B of the Ladybug FRQ presents a situation in which one of two ladybugs on a rotating disc, Ladybug A, begins walking in a circular path in the same direction as the disc's rotation. The question then asks if the angular momentum of the disc increases, decreases, or stays the same. The answer I chose was that the angular momentum stays the same, which is wrong. To begin with, the angular momentum of the disc ladybug system is conserved. When the ladybug begins moving, it actually gains angular momentum. In order for the disc ladybug system's momentum to stay conserved, the disc's angular momentum must decrease in order to accommodate for the increase in Ladybug A's angular momentum. Part C of the Ladybug FRQ presents a situation in which a single ladybug is standing near the edge of a disc at a distance of 0.9 r from the disc's center, where r is the radius of the disc. The rotational inertia of the ladybug disc system is I1, and the disc completes one rotation in 2.5 seconds. The ladybug then walks towards the center of the disc to a distance of 0.1 r from the center of the disc and comes to a stop relative to the disc. Now the rotational inertia of the system is I2, and the disc completes one rotation every 2.0 seconds. The first part of Part C asks to derive an equation for I2 in terms of I1. To start with, we must first acknowledge that the angular momentum is conserved in the ladybug disc system. As a result, we can write down the following equation: I1 omega 1 equals I2 omega 2. We can then solve for I2 by dividing both sides by omega 2. Next, we can replace omega 1 with delta theta over 2.5 and omega 2 with delta theta over 2.0. We can see here that the two delta thetas in the equation cancel out. This leaves us with the following. This simplifies to 4/5 I2. Or 4/5 I1 actually. The second part of Part C asks if the ladybug exerts a torque on the disk when it is walking towards the center. The answer I put was that it did not, which is wrong. The reason I put this answer is because I assumed that since the ladybug was walking towards the center of the disk, that it was also applying a force in the direction towards the center of the disk. Because the force is not perpendicular to the radius, it would then be deduced that there was no torque. However, a torque is actually applied by the ladybug. This is made evident from the fact that over the course of the ladybug walking towards the center of the disk's angular speed changes from completing a full rotation in 2.5 seconds to completing a full rotation in 2.0 seconds. The only way for angular speed to change is for a torque to be applied, meaning that the ladybug must have applied an external torque to the disk as it was walking towards the center.